right, so this is our energy and heat notes, and if you do not have your Cornell Notes template open, please go do that now. It is on Google Classroom. All right, so let's get started. All right, our essential question here in these notes is what is heat capacity and how to use it? So we're going to go through a couple things of how to calculate heat. We talked about in the last notes how heat is transferred. We talked about how it works in a phase change. Now we're going to talk about, well, what happens if we're not going through a phase change? What happens when we're just talking about certain substances? All right, so a couple definitions I wanted to make sure and get out of the way. Heat. Or Q, and we call this Q heat or energy, and it's energy that transfers from one object to another, and it flows from warmer to colder, which you guys saw when you had the ice in your hand. Temperature is the measurement of energy in a substance, so it helps us measure how much energy is there. And then I'm going to introduce you into a new concept called specific heat, or sometimes we call it heat capacity. And that's how much heat or energy it takes to raise the temperature of a substance, of anything, okay? And so it can be in different measurements, but I'm going to give you the calculation of how to figure out, and sometimes you have to use this, well, you have to all the time, use the specific heat of a certain substance when you're wondering how much energy it has, okay? All right, so a little more about specific heat capacity, or C, and you'll see how it works in the equation a bit. But it's the amount of heat, and it can be in calories or joules, needed to make 1 gram of any substance that you're talking about go up 1 degree Celsius. So it's like if I'm holding in my hand 1 gram of salt. Salt has a certain specific heat capacity, and it's going to need so much energy to raise it 1 degree Celsius. And it's a lot of energy because you can hold it in your hand for a really long time without getting it too much of an increase in temperature. Okay. And different substances have different specific heat. So everything is different. And one of the things that kind of, again, like that endothermic and exothermic is kind of like a backwards way of thinking. This is the same. So if it has a low specific heat capacity, which is C, means a substance heats up fast. For an example, metal. Metals have a very low specific heat capacity. And a high specific heat capacity means that the substance heats up slow. Examples like plastic. So if I put a metal and a plastic out in the sun, of course the metal is going to heat up a whole lot faster because it takes less energy, okay, to heat it up, okay? And it takes more energy for the plastic to heat up. So that's why it has a low specific heat capacity, meaning you only need a low amount of energy to heat that substance. And a high specific heat says you need a lot of energy to heat up that substance. So I hope that makes a little bit more sense, okay? All right, this is our equation for calculating energy and heat. Q equals MC, and this is a delta. This is Greek, delta T, and I'm going to define each of these for you. This is actually on your equation sheet. You never have to memorize this equation, okay? So this is our equation, and we have energy, which I just told you is in calorie or joules. We have M, that is our mass, which is in grams. C is our specific heat capacity. We get that from a table. And delta T just means change, so change in temperature. And we usually do that in Celsius because we're not in gases anymore. Remember, gases were in Kelvin. We can use Celsius somewhere else, okay? So C, like I just said, specific heat capacity, you get that from a table. You don't need to memorize that or how to do that. M is mass in grams. Okay, and delta T is change in temperature, and it's basically the final temperature minus the initial temperature. And we'll practice these a couple times. We have some forums to go through to practice this a few times, okay? Okay, this is an example of what a table would look like. So these are examples of different specific heat capacities. So let's look. So we have high ones. Water is one of the highest. So if you think about it, if you have a pool in your backyard, it has to be really hot outside all day long to get it to start heating up, unless you have a heater. But if you turn off your heater, how long would it take? It takes weeks to heat up all that water. And that's because water has a very high specific heat capacity, which means it takes a lot of energy to raise it 1 degree, just 1 degree Celsius. So you can see it's got a 4.186. Ice was a 2.1, so you had at least 2.1, and this is kilojoules, okay? 2.1 kilojoules in your hand to get it there. Steam, 2.1. Glass is extremely low. So, of course, glass gets really hot really fast. So you can put it down. Mercury is even faster or lower, okay? So it heats up even faster. So as these numbers go down for you, hydrogen has a super high energy. So it needs a ton of energy to heat up, okay? And 1.8. So wood is kind of in the middle, right? Kind of, okay? It's higher. But you can see steel, of course, steel. If it's outside in the sun, bam, it just burns you really fast, right? And aluminum, okay? So remember, the lower the specific heat, the less energy it needs to get hot, okay? All right, so we're going to do a couple practice problems here. We do have some Google Forms for you to practice, but remember our equation is Q equals mass times specific heat times delta T. So the biggest thing is to start identifying what is what. Remember I said those units are kind of important because they're going to help you identify things. But it says calculate the amount of energy in joules required to heat 145 grams of water. So this is in grams, so this is definitely our mass of water from 22.3 degrees Celsius, so this is our temperature, to 75. So 75 is our final temperature, and this is our initial. So when we're calculating delta T, it's going to be, delta T will be 75 minus 22.3, okay? So our delta T is going to be 52.7, okay? Now we know our mass, okay? It is 145 degrees. Now, it's telling me of water, so I need the specific heat of water. So I will go back up, okay, to my table, and I will go, okay, well, I have water. What's my specific heat of water? Well, you can see it's 4.186. You don't have to calculate that. That would be given to you, okay, in a table. So if we do that, then we plug everything in, 145 times 4.18 times 52.7. So go ahead, take a minute and calculate that. I hope you got 31,900 joules. Okay. All right. So hopefully that made a little more sense. We're going to practice that more. But I want to get into, we've talked about heat and we talked about energy, but there's a specific thing about phase changes. And this is really, remember when we talked about the melting point, boiling point. So we call it, and there's special names for it, and H of F. So this is what we call the heat of fusion. Remember when we looked at that graph and we looked at when it got up to the 0 degrees when we're going from ice to liquid, okay? That is called the heat of fusion. That is how much heat we needed to get to that point for it to start converting from ice to liquid. And so there's a special equation that we use when we're starting to think about the heat of fusion, and that's just going from a solid to a liquid. And it's the energy used to melt or freeze. So at this point, you could do it melting or freezing a substance already at the melting point or freezing point. Okay, so formula. Note, there's no temperature change. Remember how the graph was completely flat when we're going from a solid to a liquid? And this is our equation. And this is how we calculate Q when we're talking about a phase change. The other one we just did in the practice, there's no phase changes. We didn't talk about phase change. It's just raising the temperature of a substance. When we're talking about phase changes, then we have our special equations. And these are also on your equation sheet. But the amount of energy it's going to take, and then we do heat of fusion times mass. So we don't have a specific heat. We don't have delta T, because remember, we're going through a phase change, so temperature is held constant, so it'd be 0 anyways. All we need is the heat of fusion, which is something from a table, and the mass. So that's how we would calculate when we're going from ice to liquid, if you think about it, because we're just really going to deal with water, but a solid to a liquid. Okay. And we always use calories or joules. This is on a chart, and of course, mass is usually in grams. The other phase change that we talked about in that graph, if you can remember, so you had that first flat line. Then it started heating up as it got to liquid. So the liquid started heating up and it started hitting to the point where it starts turning to gas. And that's called the heat of vaporization. And we do it like this, H of V. And this is going from liquid to a vapor or a liquid to a gas, okay? So it's the energy used to boil or condense a substance. So heat of vaporization, it can work either way. It's going forwards or backwards, okay? Already at the boiling point or condensation point. And remember, when we're at that flat line, there's no temperature change. So that's why we're not even dealing with a delta T or change in temperature. And again, our equation for this one would be energy equals heat of vaporization times mass. So when we're doing these calculations, the biggest thing when you're using these heat of vaporization and heat of fusion is to identify, am I going from a solid to a liquid or am I going from a liquid to a gas? That is the big point, because then that'll tell me if I'm going from a solid to a liquid, I'm using the heat of fusion. If I'm going from a liquid to a gas, I'm using heat of vaporization, okay? All right, so here's a sample problem for heat of fusion. So remember, our equation is Q equals heat of fusion times mass. So calculate the amount of energy in joules required to freeze. Freeze right there tells you you are at the point where you're going from a liquid to a solid. So that's where you would use heat of fusion to freeze 145 grams of water. And the heat of fusion of water is 334 joules per gram. Well, if we look here, Q is going to equal the heat of fusion, which is this one right here, times our mass. So you'll just plug those in, okay? And you'll multiply them to get 48,400. So go ahead, check my math, make sure I'm right. If I'm not, let me know, okay? So the second problem I'm going to give you is, how about heat of vaporization? So again, it's Q equals heat of vaporization times mass. How much energy must be removed to condense? So again, that tells me condense. That means I'm going from a gas to a liquid. So that means I'm using the heat of vaporization. And it gives me my mass, okay? And it gave me the heat. I don't think we gave you the heat of vaporization, but it is 2,260 joules per gram, okay? And this would be given to you, the heat of vaporization, okay? Times the mass, 146.7, multiply amount, I need 331,500 joules of heat to go from a gas to a liquid, okay? All right, so go back to your notes. We're going to practice all of these equations more in class, but go back and highlight some important information that you had there. Make connections with your notes. Write any questions in the left column. I'm assuming most of you probably have questions. And then I want you to go and write a 3 to 5 sentence summary of your notes. All right, and with your questions, please feel free to email them to me, and I will be happy to answer them. All right, well, I'll see you next time.